Power is one of the most fundamental problems we as engineers must solve in any of our designs. Not only from the standpoint of maximizing efficiency, minimizing size, and achieving the requirements of our system, but also in keeping costs and design complexity low. This reality becomes more strident when we're dealing with AC to DC power conversion, where many off-the-shelf power supplies can greatly simplify our designs. Is there still a place for designing our own discrete AC to DC power supplies? And if so, how can we as engineers see the best path? So I remember when I first started college as an electrical engineer, I think probably the first lab that I did, and I'm sure most of us did, was sitting down and actually designing and building my own AC to DC power supply and getting the transformer and all the circuitry correct, putting that in a box and then having a couple different output voltages available on that. And it really was when I first fell in love with that whole concept of designing power supplies. And I think for me, as more of a digital engineer, also when I fell in love with getting AC to DC as quickly as possible, where I could use it and have a lot more fun with it. Today as engineers, we a lot of times we'll go and look to see, should we design our own AC to DC power supply, or is there an option for us off the shelf? And there's so many different wall warts out there, and off the shelf AC to DC power supplies in the 50 watt, 100 watt, 200 watt range, that it often can be a little bit of a challenge to see the need for us to ever do discrete AC to DC power supplies outside of a need for something very, very unique. But I think there is a place for it still. And today I've got the opportunity to speak with Doug Bailey, who's the Vice President of Marketing at Power Integrations, and a fellow engineer who spent a lot of time looking at AC/DC power supplies and building the circuitry for those power supplies. And I think he has a lot of great insights on when it can make sense for us as engineers to do our own discrete designs. Doug, thanks so much for joining me on The Current today.
Well, thanks. Thank you for having me, Todd.
Yeah, really, really appreciate it. So let's kind of start with the elephant in the room, and I've already mentioned it a little bit. There's certainly a lot of very low-cost, off-the-shelf power supplies out there these days. So I think for us as engineers, it sometimes can be a challenge to think, okay, how am I going to justify doing my own design? Does that make sense? Can I really do it cheaper than what I can buy off the shelf? And can I do it more efficiently from a time perspective than just buying something off the shelf? How do you speak with engineers about that, and what advice would you give?
Yeah, I think, as you pointed out earlier, the world of power supplies has changed since you were in school, and certainly since I was in school.
Longer ago than I like to admit, Doug.
Yeah, winding those a linear transformer followed by a 7805 or something like that. Those were simpler times, and power supplies are no longer like that. We don't have any fundamental belief or zealotry about whether people should buy or make power supplies, and there's a very good reason for that, and that is that most of the people who make power supplies buy chips from us anyway. So
Right.
yeah, we sell it one way or another. But your point is well made about can you just, or is it appropriate to just buy the cheapest power supply out there? And I would counter with quality and reliability are just another parameter. People sometimes make it a sort of subjective judgment about those things, but it's horses for courses. You don't need a high quality power supply if you're designing Dancing Santa Claus. It's going to be used for 20 minutes at Christmas. But you do need one. You need a very, very high reliability power supply if it's going into a life critical application, medical or aerospace or even automotive. So, it's just a parameter.
Right. And I think that gets into my next question, and you kind of mentioned it, I think already, what are the applications where we should be looking at our own discrete power supplies? And so you already mentioned, if it's just some widget that's going to go, out a Christmas ornament or a yard decoration or something that's out for maybe a month, might not make sense. But if it is something where it's got to go into an automotive safety application, maybe a large piece of industrial equipment, what applications do you see engineers more typically using power integrations for those discrete designs?
Yeah, I think it depends most on volume and what your customization requirements are. It costs a lot to design a power supply. You have to have an engineer design it. You've got to have component engineers, manufacturing guys. You've got to set up a line, or find a contract manufacturer who's willing to set up a line. You got to have test programs and rework capability and reliability, quality, FCC approvals, or other radiated EMI problems you've got to deal with. So it's not simple, and there may be multiple regulatory bodies, multiple tests worldwide, voltages as well as regulatory activity. So it's not cheap. But on the other hand, what can happen if you do your own power supply is you can customize it more precisely for the needs of your application space. So if you've got multiple outputs, or if you've got a high reliability requirement, or you've got, you really want a little bit of extra assurance of robustness. If you're in control of your own power supply design, you can make sure that gets built into the product. So you've got to trade off this sort of fixed cost of development against potentially cost of ownership if you think you can make it cheaper, or the cost of ownership, or the capability that the custom power supply provides to you in the end application.
Right. Certainly. And so I think those are some of the things we've got to take into consideration when we start our power supply design is, what is going to be required in the end product? Are there certain certifications that we have to go through? Are there any, things that you really think that an engineer should be taking into account outside of those basics when they're starting an AC/DC power supply design? Are there any common pitfalls that you see engineers running into in these designs that you could help them avoid?
Yeah, I think the first challenge that most people have with a switch mode power supply design is the transformer design.
Right.
It's so critical to the efficiency, the performance, whether you're going to have safety problems getting certification, whether you're going to have problems with ESD, or other, what I refer to as kind of secondary spec items, but they're still primary when you want to make something in production, right? You still got to pass.
Right.
They're the things that you don't necessarily think about. You're thinking about volts and amps when you dive into designing your power supply, but the volts and amps really end up being the easy part. So we help customers with that with a tool, and what our tool does, it's a very sophisticated chooser. It's very popular these days to say AI. It's not AI. It's just a very complicated algorithm.
Right.
But what it does is it designs the transformer for you, and it builds in an understanding of the first the volts and amps, but then also things like reliability, safety, and EMI, audible noise,
Right.
And all these kinds of functions that somebody who's not necessarily completely immersed in power supplies all day, every day, you may not think about it. So we do it with a tool.
Right. Is that a tool that you make available to the customer base, or is that something that you guys use internally? How does that work?
Well, we do use it internally. Our engineers in my applications organization use it. Our field applications people use it, but it's available online also. So it's in two forms. You can download it, or you can access it through the website.
Excellent. And I know that that's something that we've seen a lot of engineers be successful with, and being able to go onto the PI website and utilize that for the transformer design, huge benefit when you're doing something. I think the other thing that we've seen with power supply designs lately is that, as opposed to, again, going back 25 years ago and doing a silicon design, now there's the other consideration and complexity that engineers have to bring in is, should I do it with silicon, or do I have an opportunity to improve the efficiency of my power supply by doing the design with wide bandgap technologies? And I've been really impressed with what I've seen, the efficiency levels I've seen a lot of engineers be able to get out of that with wide band gap. Obviously, they're more expensive than using silicon, but when do you think that it's worthwhile for an engineer to start considering a silicon carbide or a GaN solution as opposed to traditional silicon?
Yeah, that's an excellent question. In terms of, I might challenge you a little bit on the cost, and the reason for that is the answer is it depends. Uh, Gallium nitride per se is more expensive, but
Right.
when you look at it at the system level, you can make substantial system savings, and one of the things that you save on is heat sinking
Yeah.
because you're not generating the heat, so you don't have to get rid of the heat. You can often save on the PCB because you can make that smaller. You can save on the transformer. You maybe move some of the heat that used to be in the transformer. You can move it to the switch because the switch isn't generating its own, right? So now you can
Right.
use some of the tools in the PI Expert I was talking about to shift where the energy losses are. So ultimately, a GaN solution is not necessarily more expensive than a silicon solution. Plus, it can do more. We have a device available now that's 95% efficient in a sort of 100 watt plus application flyback. So it's very
Right.
simple to design because it's a flyback. It can do variable voltage inputs and outputs because it's a flyback. You're not dealing with resonance and all the nasty dynamic range problems that resonance brings for you.
Right.
Um, and that 95% includes a bridge. So you can imagine there's not an awful lot of energy being burned anywhere else. So
Right.
they have such advantages to using GaN, and there are really no disadvantages, with the possible exception of cost for the device itself, which is generally speaking a little bit more money. Um,
Right.
so then the other great thing about GaN is robustness. Um, it's a new technology, and so new technology is a little scary, and people worry a little bit about the new technology. But what we've been able to show is that there's so much voltage margin with GaN. It doesn't have a, a classic avalanche mechanism in it.
Right.
So you tend to make them very, very high breakdown compared to their rated breakdown. So
Right.
they're extremely robust to voltage. We haven't found any mechanical or chemical degradation mechanisms either, and so these things do very well from a reliability point of view. So
Right.
there's really no reason not to use GaN. Um,
Right.
we have silicon carbide as well. We have a product called InnoSwitch 3 that has silicon, GaN, and silicon carbide. And that's interesting for a couple of reasons. But one way it's particularly interesting for an engineer is that we can build a power supply with all three and see how they work, right? See what the efficiency
Right.
curves are. So it gives you a controlled experiment, same package, same control algorithm. The only thing that changes is the switch, and it's a very interesting piece of data. And it turns out that GaN is actually slightly more efficient than silicon carbide. Silicon carbides
Okay.
and GaN are much more efficient than silicon. And then the silicon
Right.
carbide allows you to go up to almost to over 1700 volts
Right.
breakdown.
Right.
So the silicon carbide's tough, and the GaN is goes up to 1250 volts. So that's pretty tough. And then the silicon tops out at 900 volts.
Right. Right. It's certainly a great way to quickly do a proof of concept on what efficiencies you can actually achieve from your power supply design by doing that. That's absolutely incredible. I haven't I didn't realize that. That's really good to know. So you've got a ton of engineers at Power Integrations that are doing just this all day, and so the expertise that you guys have amassed is really incredible. We talked about some of the online tools that you have to help with power supply design. What other capabilities and tools does Power Integrations have available to engineers to make AC to DC power supply design easier?
Yeah, we have about 1,000 reference designs on our website. So
Right.
we've been labeling these things sequentially, certainly since I joined the company about 20 years ago, and we just keep adding to them. We've got up to about reference design 1089 or something. I think it's our latest one. So over 1,000 reference designs, and that's a vast library of generally highly application specific designs. So they were designed with some purpose in mind, whether it was an adapter or USB PD adapter, or whether it was a refrigerator, main power, or even something simple for a toaster, or a clock radio or something. So we've got so many of those, and there's a sorting tool on the website where you can filter out the various things and look for the voltage input you want, how many outputs you want, and it will serve up the relevant reference designs.
Right. Yeah, that's absolutely been incredible. I know one of the other things that we've used a lot is you've got a team of engineers there in Montreal and a lab that I know we've used a lot of out of our corporate headquarters to help us with designs for customers also. And so I think between the online expertise that you have and the library of designs that are really ready to go, just for maybe whatever tweaks we as engineers might need in our designs, or the engineering labs that you've got that, we at Future would be happy to plug our customers into, and have conversations with those engineers. We can absolutely help other engineers be very successful in AC to DC power supply design with Power Integrations products very quickly. And I think the offering that you've got, and we've only been able to just basically brush over the top of it in today's conversation, it really is incredible. And I think that the game is changing, particularly with things like wide band gap becoming more and more of a focus for a lot of engineers these days.
Yeah, you can't overestimate the effect and that having a really strong FAE crew can have on customers.
Yeah.
So your guys I know are extremely strong, and you attend our annual FAE conferences, and you send representatives, in fact several representatives to the last one, which was great. We have field applications engineers that are direct PI employees in all of our major territories. We have a ratio of about 2-to-1 of FAEs to sales guys, and so that is very, very helpful for supporting customers. The customers should be able to get the help they need from a live human. We also have a dial-in capability called Power Pros. And those guys they're actually in the Philippines, and they're resident with our huge applications activity in Manila. So they can, if they can't answer the question themselves, they can go and find one of the more senior apps guys and go get an answer, or somebody who's a bit more specialized and go get an answer. But they're on the phone, they're manned 24/7, 365. There'll be somebody there to take a call and answer a question from an engineer who's struggling with a design or needs help selecting a device, or otherwise wants to chat about how to debug a power supply. They can drive PI expert for a customer if a customer would like a custom design done.
Right. Or like you said, with 1,000 different reference designs and a library of 1,000 reference designs, maybe help dig through that. That's a lot of designs to find what exactly you're looking for. So
yeah.
Definitely very impressive. Well, Doug, again, thank you so much for the time. This has been a really useful conversation. I think, the make versus buy conversation is one that we have so often with engineers these days, and one that we've got to continue to be looking at and find the innovative ways that we can continue to make designs better. As you said, we've got access to Power Integrations FAE team, who are absolutely phenomenal and true experts in this. Future Electronics also has our specialist team of engineers. We have our general engineers, but then we all have a team of just Future Power Solutions engineers that we can sit down with you and also help with your designs. So thank you so much to our audience for listening to The Current today. Doug, thank you so much for joining us. If you are listening to us today and you have an interest in doing your own AC to DC power supply design and would like to talk to fellow engineers at Power Integrations, at Future Electronics, we would love to speak with you. Please feel free to reach out to us at Shaping the Future. That's one word, Shaping the Future, at futureelectronics.com. And we would love to join you and help you out with your designs. Thanks again so much for joining us on The Current, and we'll see you next time.
Thank you.